Hello everyone, my name is Felienne Hermans. I'm assistant professor at Delft University of Technology. I'm on Twitter as well, so if you want to rate me not through the app but by sending a tweet, then feel free to do so. So maybe you're wondering at a developers conference why we are talking about spreadsheets. So my view on this is spreadsheets are definitely mislabeled. Many people think of spreadsheets as being data. But spreadsheets are not data. Spreadsheets are code. This is the gospel of my life. Spreadsheets are code. I go to all sorts of conferences to share the happy word that spreadsheets are code. So if you want to leave now or fall asleep or do some email, that's fine, because this is already the most important message of my talk right there. Spreadsheets are code. So you might wonder why. Well, I have 3 reasons for this. The first reason that spreadsheets are code is they're used for similar problems. As you see here, this is an investment calculation where you put in some numbers and an investment advice comes out. You could make this in any programming language. I mean, you could do it in C or in Objective-C if you want an iPad app, or in Java, or in a spreadsheet. It doesn't really matter. There's nothing special about this problem that makes it spreadsheet specific. Of course, you could wonder, why do people do this in a spreadsheet? I have asked people this. So during my PhD dissertation, I've worked with several banks and investment companies in the Netherlands, and I asked them, like, why are you building this? Why aren't you, asking your IT provider for some software? You know why? Because we are bad at making software. Seriously, they have tried this. They've went to their IT provider, either internally or externally, and they say, look, I've made this spreadsheet and it's sort of okay, it's like a prototype. Can you build me some software for that? And the IT provider goes like, yeah, sure, no problem. That'll be 6 months and €1 million. And if that were only true, it wouldn't be that bad, but it's never 6 months and €1 million. It's 9 months and it's €3 million, and it has half the features they want. So end users perceive themselves as better programmers than us. And I mean, they're not entirely wrong in that, because they can quickly build prototypes that do what they want. So I go to great lengths to make my point. To such great lengths, in fact, that I have built a Turing machine in Excel formulas to show that spreadsheet formulas are Turing complete. So no more saying, please, that spreadsheet are not a real programming language, because this is a Turing machine. Every row, by the way, is 1 iteration of the tape. And with conditional formatting, I'm moving the head over the tape. So it's also, I think, a nice visualization of a Turing machine. You can easily see what's going on. You see the history stored in the rows as well, instead of just the head moving over a real tape. And many people enjoyed this a lot. It sort of went viral on the internet. And it brought my personal blog down for half a day, because it was on Hacker News and on Reddit. So the third reason that spreadsheets should absolutely be treated as pieces of source code is they suffer from typical software engineering problems. Only 1 in 3 spreadsheets has a manual. An average spreadsheet is used by 12 different people over a lifespan of 5 years. Does that sound familiar? That is exactly the type of problems that software is suffering from, and especially was suffering from, let's say, 30 or 20 years ago. In those days, everyone was an end user. There were no software engineering degrees yet. There were no tools. Everyone was just building their own stuff. And then software engineering, software suffered from those problems as well, and spreadsheets still do today. So in summary, the activities, the complexity, and the problems surrounding spreadsheets are the same as software. So spreadsheets are code. There's no denying it anymore. But I'm going to go further than that. It's not just a programming language. Excel actually is the next programming language you should learn. Why? Resistance is futile. Why? First of all, spreadsheets are live programming. Who knows who made this? Is anyone familiar with this picture? Yeah, who made it? Do you know? Oh, it's okay. So it's made by a guy called Brett Victor, and what he proposes here is the idea of live programming. So on the left side, you have the instantiation of the source code that you see on the right. So if you change something here, a number, a color, or an integer, the tree will change immediately. So there's no compiling involved. It live updates. And he coins this term live programming. Well, that's awesome, Brad Victor, but we had that since VisiCalc. I mean, a spreadsheet is live programming. You change your formula and automatically everything updates. There's no compilation involved there either. So functional programming is sort of like back from the almost dead. It's getting more and more mainstream. So you know what else is pure functional programming? Excel is pure functional programming. A formula in Excel is, by definition, side effect free. The only thing a formula can do is take input from different formulas and produce a value. A formula cannot change the results of another formula or another cell. So there are no side effects. Isn't that fantastic? Thirdly, everyone knows spreadsheets, people. Everyone, like your neighbor is managing his soccer team's finances in a spreadsheet. Your accountant is probably doing your taxes in a spreadsheet. Everyone knows spreadsheets except us developers. Isn't that sort of sad? I really like to say that spreadsheets are the most successful programming language in the history of mankind. It's such a good programming language that people don't even know they're programming. Isn't that fantastic? I mean, imagine doing Java by accident. That will never happen. When people are programming in a spreadsheet without even knowing they're programming. How successful is that? So I'm going to assume now that you're convinced that spreadsheets are code and that you're also convinced that spreadsheets are pretty cool. So let me show you some typical programming ideas implemented in a spreadsheet to show you how super awesome they are. Let's go. So Uncle Bob says that functional programming is programming without assignment statements. So let's see how that looks like in a spreadsheet. We are going to take a typical example. We're going to square some integers. Let's take it easy. I know it's late in the day. So I have a number of values here. And what I want is the square. So that is still pretty easy. What I can do is I just multiply the number with itself. And I can drag that down. Probably you know this. You can drag a formula down, and then it automatically updates the location. You can also double-click there, and then it goes automatically. So what we have is a list of inputs, and we have a function definition. This is just defining a function over an input. It's like a map. We're mapping the function over all the inputs. But now you're going to say, as developers, this isn't pretty, because all those formulas look slightly different. But I can fix that. I can give that first column a name. I'm going to call that input. And what I can do now is I can refer to that named range in this way. I'm dragging this input down, and what happens now is every value in this range gets the value that's the intersection of this row and the named range. So I can delete that, and what I can do now there, instead of referring directly to the formula, I can say input times input. Isn't that nice? And now it looks like more proper programming. That's cool, huh? It's the same everywhere. So it's really like a function, and you can do that without having the ugly spreadsheet-like A2 and A3. So let's do something a little bit more exciting, because this is still quite easy. So what we'd like to have is the sum of all squares that are over 30. So I can make a simple Boolean. I'm going to say which of those values is bigger than 30. That's still, super easy. And see, we have square here. So again, here, everywhere we have a nice, consistent formula. No A3s and A7s, just a nice formula. We can use a sum if now to sum all of the values in the squares over 30. It's sort of nice syntax, sum if over 30. If this is true, then I'm summing the square value. But it takes a lot of real estate. There's a lot of room I need for all those extra squares and extra booleans. So what I would want to do is something a little bit more efficient. What I would like to do is I would like to multiply those two ranges directly. So multiply the squares with the boolean that internally is rewritten to a 0 or a 1, so you can multiply with it. What I could do is multiply input by input. But that's not it, because what I showed you earlier is if you have a range, if you refer to the range, you get the intersection of the row and that range. So that's not what we want, but it is close. What we can do is use Control-Shift, and then Excel makes this into an array function. And that means we can calculate with ranges or arrays as first-class citizens. So if I just type the same formula and hit Control-Shift-Enter, I get this. And I get a different value. See, without curlies, it's this, and with curlies, it's this. What's happening here is this entire input range is multiplied by an entire second input range, and the result of those two ranges, because it's pairwise multiplication, is another range. So what we're seeing here is the first item of the result of this range multiplied by itself. And if I would give it a little bit of space, I would get the entire array, or I'm just going to show you, I think, the first 5 elements. So I'm copying this formula now here, and then we get the first 5 elements of that array. So now you can see that that array formula actually results in a real second array of which I'm showing a few values. What I can do then is I can reduce that array. So I have all the values now. I could sum it. So I could do this. The sum of this range multiplied by itself. So in just one formula, we don't need all the extra cells, just in one formula, I'm multiplying the range pairwise with itself, and then I'm summing everything. And there I can also put in the filter. I can multiply input by input, and then multiply it by whether or not that is bigger than 30. And then I get the same value here, but I could delete all those extra cells. I don't need them because everything is reduced. So it's pretty efficient if you know about all these special functions like array formulas. So something else I want to talk about is how error values work in Excel. Probably you've never really thought about it because they are so intuitive and nice, but there's something interesting going on there. So suppose, again, you have a number of inputs, and I'm going to seed this with some random data between 0 and 3. So sometimes we get zeros there. Suppose I would want to divide by that random data column. And I'm going to call that the danger zone, because it's really very dangerous, because they could be 0. Look at that. Danger, dividing by 0. Excel warns us. Excel gives an error and says, oh, watch out, this is an error. So think about this for a minute. What is the data type if we're saying this is an integer? What is the data type of that range? Who's a functional programmer here? Yes! Look at this, guys. It's a monad in Excel. It's a maybe int. This is 700 million Excel users. They just use monads without any problems. They don't even think about it. Because if we have another column that uses this maybe int as an input, it just works. Look, we have here a calculate some more column that just takes the maybe int and works with it without any problem. So this plus here is lifted and just applied to the int. So we go from a plus that works on integers seamlessly to a plus that works on maybe an integer or an error value. Isn't that awesome? I think it's pretty cool. So let's do some more real programming, because now you're saying, yeah, but a little bit of filtering, a little bit of summing, that's not something that I'm really going to use. Let's tackle a bit more exciting problem. So what we have here is a maze, and it's filled with money. So I want to have a walk through this maze that gives me most money. I'm a poor academic, so I need to get my money from programming examples that are set in a maze. So what I could do, of course, what would just work is I could define a recursive solution. I'm going to start here. So this is the beginning of my maze, but it's easier to start at the end and work our way back. So what we can do is we can say the value, what we can achieve most, what the most money is that we can get from our maze. There are two options. Either I came from that way, or I came from that way. That's the only two options that could have happened if I have reached the end of the maze. So I'm simply going to take the maximum of those two. So the maximum that I could achieve here, or the maximum that I could achieve there. The maximum of those two paths through the maze. So this is a solution that works. However, there is a problem with this solution. Does anyone know what our problem is? Yeah, so it's not very efficient. Yes, it's not very efficient. It's not really solved. It is solved, but it's not really solved because, for example, this path through the maze, every recursive call, you would try all the paths. Next recursive call, so if you're here, you try all the paths, and then you're here and you try all the paths. So it works, but it's very expensive because you keep exploring the entire maze. So what we could use here is a technique called dynamic programming. And what dynamic programming does is it saves half states of the problem in order to be more efficient. You don't have to calculate everything. You calculate subproblems. You calculate the whole problem from subproblems. So here is our maze, and we're going to have an extra worksheet called max. And what we're saving there is the maximum value at that square in the maze. So those are easy. This one and that one, there's only one way you can reach that square. The only way to get there is like that, because we're only moving that way. So those are easy. But the rest of the maze, what I want to do there is I want to look at what is the best way I could have achieved this subproblem so far. So I'm taking the maximum of those two steps before me plus whatever is in this field of the maze. So either I came from that way or I came from that way plus whatever was already there. Now I have the same formula for all those squares in the maze. And I have my answer. That's it. That's the whole solution. And if you compare that to, this is a very famous problem in computer science, with the solution in C, or even in Haskell, it really looks very easy in a spreadsheet. This is the only formula you need for the entire maze, and you have your answer. However, it's a bit cumbersome, because now I have the value, but what I also, of course, would want to know is what is the path through the maze? How am I supposed to walk in order to obtain all that money? And of course, I could find it out, because every time I could look, what is the best of those two, and then what is the best of those two, and I could retrace my steps. But that's too much work. I'd rather have Excel do the thinking for me than I do it myself. So what I'm going to do is, instead of printing the values, I'm going to print the paths with arrow-like symbols. And those arrow-like symbols are going to indicate how I'm walking through the maze. So here, it's relatively easy. Because again, if we're on the border of the maze, there's just one way we could go, up, and in this case, left. Those are the only options we have, because we're only walking, now we're walking back, so we're only walking up. Then in this case, if I want to detect where I was coming from in my optimal solution, I can just say, well, I'm going to point at the maximum. If the maximum is above me, I'm going to print this. And if the maximum is next to me, I'm going to print that. And now we have sort of a vector field of our maze. Looks interesting, and I could say it's solved because I can just follow the arrows. Now I could go like this, that way, and then that way. That's how we're going. But still, it's too much thinking. So let's just tweak the formula a little bit such that the solution looks somewhat nicer. I'm only going to print something if the cell is being pointed at. Only if I'm really in the path, I'm printing, and otherwise I just print the empty string, because that will look very pretty. So there we go. If the value below me is this, if I'm being pointed at from the bottom, then I'm printing something, and otherwise I'm printing the empty string. Still, sort of an easy formula, and it looks nice, but we're only going one way now. You see, we're only going up, and the first path we have from here is now stalled. So we need one more thing, because now we're only pointed at from below. We also want to print if we're pointed at from the side. Almost the same. We just add this. We're just saying if the value next to us is that arrow, we're printing as well. And otherwise, it's the empty string. And then we get this. Ta-da! That's our fad, our money-making fad, through the whole maze. And it's really a very easy formula. It's just, if I'm being pointed at, I'm going to print the maximum, and otherwise I print the empty string. And the nice added value that you see now, the power of live programming and having the data and the formulas together, is that every step of the way, it was very clear what was happening. Now I'm printing values, now I'm printing strings. You're very in touch with your data. Whereas if you're doing this by reading from a text file, probably you're using pen and paper to track, okay, what am I printing, what am I doing? There's print statements everywhere, or you're using the debugger. You have to spend lots of effort to remain in touch with your data, whereas here, the data is right there. It's screaming at you, like, use me, give me some formulas, and I will tell you what I'm up to. And that makes spreadsheet programming really very, very easy and intuitive. So in summary, spreadsheets are code. If anyone close to you says, it's just a spreadsheet, hit them on the head with something, really. Tell them it's untrue. Spreadsheets are real programming, and it's super cool. So of course, this is sort of the main idea behind all the research I'm doing at Delft University of Technology is, if spreadsheets are code, then maybe they need some software engineering. Maybe we as software engineers know how to support people that are building spreadsheets. Because in software, as I said in the beginning of my talk, 30 years ago, 25 years ago, everyone was an end-user programming, everyone was building their own compiler, and then 10 years later, people were like, oh, yeah, no, that program is still running. Probably we've lost the compiler, and also the person that built it isn't working here anymore. I don't know either. So we saw those problems, and we realized as a community, we need to improve. We need to build some tools to help people maintain legacy code. So if you look at a modern IDE, well, this screenshot isn't all that modern anymore, but if you look at a IDE, you see it has all sorts of features like debugging and testing and analyzing. Those features are not helping me to build code, to write code. They're helping me to write responsible code, to be a good developer. I'm going to test my code. I'm going to analyze code metrics from now and then. It's helping me to be a good developer. Then, if I look at Excel, yeah, it has support for making things a different font or a different color. It has no support for anything, no IDE-like features helping spreadsheet developers to build good spreadsheets. So whether they have the first version of the first example I showed you with A2 times A3, or they use nice names for everything, no one, at least not the interface, is telling them, maybe you shouldn't call everything A5, maybe you should give some names here and there. So because spreadsheets are so similar to source code, is what I observed, maybe we can help spreadsheet developers with some ideas from software engineering. So one of the things I built in my PhD dissertation is the idea of code smells for spreadsheet formulas. For example, the long method smell. If you have a method that's very long, that does lots of things, it easily translates to a long formula. If you have a formula, and then we're not really saying long in terms of real length, but we're looking at the number of different operations. So in this formula, we're summing and multiplying and dividing. If a lot is going on in a formula, it's just as smelly, and for the same reason as a long method is smelly. Another smell we know from source code is the many parameter smell. You have a method, and it has all these knobs and buttons you can press. That's not very maintainable. Well, and if you look at the spreadsheet formula, it's referring to that and that and that and that. Very, very hard to read. Conditional complexity is a smell. It exactly translates to spreadsheets. We have an if, so you can nest them. And there used to be a limit, I think, of 7 layers of nesting, but for reasons unknown to me, they have lifted that ban, so you can now nest up to, I don't know, 64 depth or something like that. So this really happens, that people nest 6, 7, 8 ifs. Well, if you have to debug that, it's just horrible. Something we also inspected is the use or the occurrence of clones. Like, we know clones in source code can be bad, because if you have the same functionality in multiple places, if you have to make a change, it has to be changed everywhere. This happens in Excel as well. For example, in this formula, you have this sub-formula that occurs twice. And this is not just bad for maintainability, but actually also for execution speed of Excel, because the way the Excel caching model works is Excel caches cell results, but it doesn't cache all sub-formulas. So the execution engine in this case would be like, oh, you want to have the exponent of 0 minus G36 times C36? No problem, calculate. And then it would be there. And then again, it would think, oh, the exponent of 0 minus G36. It would not remember that has already been calculated. So if you would extract that subpart into a cell, you would also get the added benefit of more speed, because it's only calculated once. So we found that those smells not only occur at the formula level. We have a tool that visualizes dependencies between worksheets, as you can see here. So the blocks are worksheets, and the arrows connect worksheets. So if there's a formula here, there would be a formula in calculation 2 that would say input A1 times 12 or something like that. So unfortunately, not all visualizations looked as structured as this one. Some visualizations look like this, still okay-ish. Some visualizations look like this, which is particularly interesting. You can't read it, but these are the 3 quarters, 2, 3, and 4 with their corresponding months. But this is Q1 with January, February, and March. So it somehow had a different structure than all the other months. And when we asked the person that built this, he said, yeah, I started like a prototype in Q1, and I didn't really know what I wanted yet. And then in Q2, of course, I started all afresh, and then I really knew how to build my model. But then, of course, time went by, and as it goes, it became January again. And I totally forgot that first quarter was like back of a napkin, I don't know what I'm building yet, and the model stayed alive with those 2 different calculations. So how would you know without a visualization tool like this? Other visualizations look like this, also interesting. So that's Dutch for sheet 1 and sheet 2. You can't really see, but this is an arrow going both ways. So all the data went from the one worksheet to the other. And what happened there was that the worksheet had the same structure, and all these formulas were connecting, and all the formulas in the other side were connecting of the same worksheet. So there was definitely an opportunity there to restructure. We saw visualization like this, where the pinkish blocks are external worksheets. So this spreadsheet is referring to different worksheets in different files. So they called this thing the mother sheet, where we got it from. And the whole process around it was people emailing someone spreadsheets. They were put in a special folder, and then you open the spreadsheet, and it would read all the other spreadsheets. Yeah, exactly. It was very wobbly, to say the least. So we concluded that those smells don't really occur only at individual formula level, but you can also have inter-worksheet smells, like you can also have inter-class smells. So who knows what smell these classes are exhibiting? When I did this talk at another conference, someone yelled bad naming. Which is true, but that wasn't what I was going for, and I was too lazy to change my slides. So it's not that. Yes, a t-shirt for you. This is the feature envy smell, because that method here, XY, it's envious, it's jealous of those wonderful fields X and Y in class A. It would rather live in class A, where the fields are that it's so interested in. So this is a smell that also easily transforms to spreadsheets. If you have a formula that refers to cells on another worksheet, then probably it's better if it would go there. This is an example from an actual open data spreadsheet set that we've analyzed. So you see formulas like this. So we're on the income statement worksheet, and we have this formula. So if my boss asks me, what does that formula actually really do? If I have to debug it, it would go like this. Okay, required funds B9. That is buildings, amount of buildings. Divided by required funds C9. That is depreciation of the buildings. Etc., etc. You have to go back and forth between all those cells all the time to really read what's going on. And we know from cognitive science that context switches are very expensive. If you have to switch views all the time, that's super annoying. So what you could do is take that formula and put it on the required funds worksheet. Just take it and copy paste it there. And the added benefit is that if you click it now, Excel will color the dependents for you, which is nice. I mean, it's still sort of a rainbow because this is actually 3 different colors green, but at least it's better because you can sort of see what's going on. And you don't need the prefixes anymore either, because you're already on the required funds worksheet. So you can drop them, which makes the formula a lot shorter. And then you start to see some structure. Oh, there are these 3 things divided by each other, plus these 3 things divided by each other. So it's really a lot better, like it is in source code, to place the formula where it belongs. Oh, you could factor out to divide by 12. Yeah, that's true. That's definitely true too. So we started a spin-off company called Infotron, and we have a tool that does this smell detection for you. Quick commercial break, where you can just upload your spreadsheet, and we tell you all the smells that are in there. So this would be how it would look like for the spreadsheet I just showed you. Well, look, there are more than 10 references to that worksheet. You should move it to a different sheet. Then, of course, if you say smells, you say, I have my hopes on you, really. Refactoring, definitely. If you have smells, then you should refactor your source code, which also goes for spreadsheets. So in addition to giving the suggestions, as we did in the beginning in the slide I showed you, we also have a refactoring tool that helps people refactor their spreadsheets. So this is how it looks like. It's called Bumblebee. And a spreadsheet user can ask, for example, for this formula. It's a simple example, but it's a sum divided by a count. So you could also use a average function. Yeah, so maybe this person isn't aware that that average function exists. Probably in this case they would be aware, but there are, for example, also refactorings we support going from a sum to a sum if, and not everyone knows what a sum if is or how it works. So you can ask Bumblebee, do you have some interesting rewrites for me? Can I improve this formula? It says, yeah, sure. We have a sum and counts to average refactoring for you. And like in modern IDEs, you get a preview as well. This is how the formula will look like if you have refactored it. And then you can apply it, and Bumblebee just applies the formula for you. And those transformations are programmable. So Bumblebee, if you downloaded it, it comes with a set of refactorings, but you can also write your own refactorings in a little language. So here, for example, is the sum and count to average refactoring. Summing a range divided by the count of the same range results in the average of that range. So we haven't tried this yet with users. If you have spreadsheet users in your company, let me know at the end of this talk. But we envision that spreadsheet users that are power users, that they can write array formulas, they maybe can write some VB. We think they could also be capable of writing those transformations themselves. And in addition, we also want to explore the idea of programming by example here a little bit, where if we observe a user is changing formulas, a few of them, we could deduce a refactoring pattern from it and say, hey, you're doing the same thing. Maybe we can apply that transformation for you in the entire spreadsheet. If you're interested to try it or want to encourage business users in your company to try it, you can download this from felienne.com/bumblebee. All the links will be also in the final slide, so you don't necessarily need to make a picture now. I'll wait for you. Then, if you say refactoring, of course, you say, that's a good one, but that's not it. Yes, testing. You're not going to refactor your spreadsheet without the security of some tests. And this is actually the... Oh, you don't believe in testing. That's a pin. Fair enough. Okay. So this is actually the chronological order in which I did the work. But it would have made sense also to start with testing, to do that at least before refactoring. However, and this was typical ivory tower thinking, I thought, yes, but how am I going to get spreadsheet users to test and convince their management to test? It's already quite hard to get professional developers to test and to give their bosses, to have them get permission for testing. But this was really thinking the wrong way, because spreadsheet users are actually quite good at testing. We observed in the same open data set I talked about earlier that these type of formulas are actually quite common. So what this expresses is if the sum of those guys, if they're 100% together, it outputs 100. But if it's not, it outputs error. This is like a test. It's like an assertion. It expresses the knowledge that those 5 things together should be 100%. And in the lack of a real testing framework, what do spreadsheet users use? Formulas. They have no other language than formulas. And we found that 8% of spreadsheets that we analyzed had these type of test formulas, so they're not all that in common. And then, of course, we thought, we could exploit those test formulas. If people are already testing a little bit, we could use that to extract a test suite. So we built another tool called Expector, and you can ask Expector to search for those type of test formulas in your spreadsheet. And then it would say, hey, look at that. I found a formula that looks a little bit like a test. And we use some heuristics there, so we have a number of words that we know that look like test outputs. So okay, error, yes, no. In real life spreadsheets, we even found test formulas outputting in a smiley or a saddy face, depending on the results of the test, definitely. So we know what a test formula is. We say, hey, what we found here is that the cell on that, the formula in that cell expresses that those guys should be 100%. And as you see, we've done some parsing here to represent the test formula in natural-ish language to make it easier for people to see it. And then you can add those formulas to the test suite. You can have the little tick mark, save the test, and then we say, well, it passed. That test passed because this is actually 100% and none of the tests failed. And then what we also do is we show users coverage of their tests. They can say, show me what's tested, and everything that's covered by a test formula is marked yellow. And this is because this is a test formula that depends on those cells. We say they are tested as well. So we're not really talking branch coverage or statement coverage here, advanced ways of coverage. We just want to give users a feel for how well everything's tested. So if you have a test, all the dependents are also tested. And the idea is, of course, if you would change one of the 20s, then that would show up. This is not foolproof, of course, because one could be there are ways you could have other cells here that depend on it. It's not foolproof, however, it is helping a little bit, giving people an idea of what's tested. What we also do is we help people then add more tests. And instead of just letting them free, we thought it might be easier to just give them one formula to test. I have 5 minutes before I'm going to a meeting. Let me add one test to my formula. So that you can pick in 3 categories: a complex formula, a formula with a big value that represents a lot of money or a lot of orders or whatever, or a formula that has many precedents, so that many cells are referring to. So you could say, for example, if you ask for a complex formula, hey, this formula here looks pretty nifty. That's probably something you want to test if you just want to add one test. And then you can express some tests, built-in tests. So you could say it's a number. This is the upper limit, the lower limit. And in a slightly newer version of the tool, we also have an extra value there where users can write a formula. So whatever formula they want, because we found this is slightly too restrictive, just having types and upper and lower bounds. And then we give people compliments. We say, wonderful, you have increased your test coverage from 6% to 8%. We want to encourage people and show them that higher coverage is indeed better. So we have added the tests, and now you see our test suite is bigger because now 3 tests have passed and still none are failing. This tool too is available from my website, felienne.com/expector. We're just at this point giving the plugins away for free because it's active research, and so no guarantees. If it doesn't work, you can send me an email, but probably there's nothing I can do about that. This is everything I wanted to share with you, but before we go over to questions, I do think we have some time for questions. We have some time for questions. Let me summarize my entire talk for you in 1 minute. So if you came in late or it's the end of the day and you're slightly sleepy, this is your second chance to get the gist of the talk in like 30 seconds. And otherwise, of course, this is optimal preparation for question asking. Spreadsheets are code. It's the most important message. Remember and tell all your friends and tweet about it and put it on a t-shirt. Why? Because they're used for similar problems. They are just as powerful, namely Turing complete, and they suffer from typical software engineering problems. Even cooler, they are what every programming language in 2016 aims to be: live and functional and used by everyone. What more is there to wish for? I've showed you a few examples of how to implement real-life programming problems in an easy way in a spreadsheet, including a nice maze solved with dynamic programming. So if spreadsheets are indeed code, they can use a little bit software engineering magic. And I've showed you that in the form of a smell detection tool, a refactoring tool, and a test tool. If you want to know more, this is the website Perfect Excel of the smell detection tool that is now commercially available. You can go to my website to download the refactoring tool and the testing tool because they're still active, ongoing research, and we really want people to try that. And I have a research group in Delft as well, where I force grad students to also like this, and you can find out more about all the sorts of research we do at our website, spreadsheetlab.org. And if you want to connect with me later, I will be at the party tonight. You can send me a tweet if you want to meet, or an email, or you can ask a question now, of course. Yeah, so one question is, what is the reach of people? What is the audience? Not everyone would use Excel like I do. Well, some people use it in way, way more advanced ways than I do with my little programming example. So of course, there are people that just use it for simple lists, but there are companies and organizations that really depend on Excel for their core business. So insurance companies, banks that really make models that the company depends on. So we do think there are lots of people that could benefit from this type of software. Yeah, that's just Excel users. So it's very hard for us to know how many people, where's the threshold of serious use? At what point, this is also, a general question for developers, at what point is it worth it to go from Notepad++ to a full-fledged IDE because you would have refactoring support? That's not a very easy question to answer, and it could also depend on your goal. Well, I'm actually in 2 weeks going to go for a research visit. I will work there for 3 months to improve Excel and to maybe also, I'm not sure if they will give me a look at the data, but yeah, they actually were one of the funders of my PhD position, so they are aware of me.